Welcome, and thank you for standing by. At this time, all participants are in listening-only mode until the question-and-answer session of today's conference. At the time, you may press star 1 on your phone to ask a question. I'd like to inform all parties today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to NASA JPL. Thank you. You may begin.
Welcome to today's InSight teleconference. I'm Raquel Villanueva with the Digital News and Media Office at NASA's Jet Propulsion Laboratory, and I will be moderating today. InSight team members from JPL in Southern California and NASA leadership are here to discuss InSight's accomplishments, share details on the spacecraft's power supply, and preview what's to come. For some background, the InSight lander arrived at Mars on November 26, 2018, and is now in its extended mission. Joining us on this teleconference are Bruce Bannert, InSight Principal Investigator at JPL, Katia Zamora Garcia, InSight Deputy Project Manager, also at JPL, and Lori Glaze, Director of the Planetary Science Division at NASA headquarters. For anyone listening who'd like to submit a question, you can do so by using the Ask NASA hashtag. For members of the media on the phone, you can ask a question by pressing star 1 and entering the queue. To access the images that we're discussing during this teleconference, visit jpl.nasa.gov/insight-update-telecon. I'll hand it over to InSight Principal Investigator Bruce Bannert to provide the big picture on InSight's activities on Mars and how the spacecraft is measuring up to its goals.
Thanks, Raquel. So as Raquel noted, we've been very busy at Mars for the last 3.5 years. We've been obtaining some unprecedented data on the deep interior of Mars as well as its weather and magnetic field. And we're here today to talk to you a little bit about some of the results that we've gotten out of that and talk about, sort of where we're going in the next few months as our power starts to dwindle. But first, before I get to that, I'd like to share some of the latest results that we have. If you could bring up B1, please. Even as our power is starting to dwindle, we're still doing great science at Mars. The animation that we're bringing up here shows the latest large Marsquake that we obtained just about 2 weeks ago, and this was the biggest event of the mission. It's a magnitude 5 event. The biggest thing that we've seen before that was a magnitude 4, which is almost 10 times smaller. So even as we're starting to get close to the end of our mission, Mars is still giving us some really amazing things to see and to add to our data record. So InSight has been obtaining data mostly from its seismometer. That's our sort of marquee instrument. And if you bring up B2, shows an image of the seismometer sitting on the surface, which is taken from our instrument context camera on InSight. This is a really super sensitive seismometer, which measures the motion of the ground, vibrations of the ground, at an incredibly precise level, down to the sort of the scale of a single atom's radius is the sort of the size of the vibrations that we can sense with this. And those vibrations come from lots of things. They come from the wind blowing around our spacecraft, but more importantly, they come from seismic waves, vibrational waves, which travel through the planet from sources elsewhere on the planet. If you'll bring up B3, B3 shows an infographic that shows some of the various aspects of the science of this mission. Down in the bottom, it shows some of the sources that create these seismic waves, either faults on the surface, which are created by forces in the crust due to mostly thermal anomalies in the interior and mantle convection, things like that. Also, possibly by impacts, and these sources create vibrations, create waves that travel through the planet. And as they travel through the planet, they are affected by the various materials that they pass through. They're reflected off of boundaries. They're refracted at boundaries. Lots of things happen to these waves, and the seismologists use techniques to decode the waves and pull from them the information that they picked up as they go through the planet. And we are able to basically we've been able to map out the inside of Mars for the very first time in history. We're able to get the size of the core. We're able to deduce something about its density and therefore the composition of the core. We've detected the bottom of the crust, and we're able to determine the thickness of the Martian crust. And we've been able to probe the mantle of Mars, and we're able to do something about its temperature structure and its mineralogical structure. And so these are the primary goals of InSight, the main goals of InSight that we actually put forth when we proposed this mission almost 10 years ago. And we've been able to meet all these goals during the course of our mission. This mission is really near and dear to my heart. It's been part of my life for even longer than 10 years. I've been trying to get a seismometer on Mars for most of my professional career. And if you bring up image B4, it shows a little bit of my personal connection. So that InSight was actually selected on my birthday. So every time InSight has a birthday, I have a birthday too. And this is a picture of the birthday cake that my wife and I baked for InSight's first birthday. And because we're nerds, we made a spherical birthday cake. And if you look at the structure of this cake, the size of the core and the thickness of the crust are actually pretty close to what InSight was able to determine many years later. So I think we had a pretty good idea of what was going on there. So as Katya will talk about in a minute, InSight's probably coming to the end of its scientific life pretty soon. But I think InSight has quite a legacy. And if you look at the last image, B5, that I have here, this is a movie showing sunrise at Mars from InSight that we took a few months ago. And I think that in a way, this is really just the start of InSight's legacy. The data that we've taken over the last 3.5 years, and will still be taking in the next couple of months, is all being archived on websites which are available to the entire scientific community of the world. And I think the data that we're taking with the InSight seismometer, its weather station, its magnetometer, and the precision tracking that we've done will be yielding scientific results with new ways of analyzing this data for decades to come. And with that, I'd like to turn it over to Katya Zamora-Garcia to talk a little bit about what the situation is on Mars with InSight.
Great. Thank you, Bruce. So the big question is, right, what does our lander look like right now as far as power consumption? If we bring up K1, please, we can see on the left-hand side, as soon as K1's up, you see on the left-hand side here, this is a selfie that was taken of the lander when we first landed back in November of 2018. So that was 3.5 years ago. You see the solar panels are nice and black. That allows us to collect energy from the sun there. And you can see upon landing, we were approximately about 5,000 watt-hours per sol for available energy to do our operations. Now, we use the term sol, and that's really referring to a Martian day, and it's different than an Earth day. It's approximately 40 minutes longer, so we do need to take that difference in time into our operations timeline. So if you look at the right-hand side today, we're at about 1/10 of that available power, approximately about 500 watt-hours per sol to do our operations. Our solar panels are now covered with some nice Martian dust there. You see it looks more of an orangish kind of color. So that limits the amount of activities we can do. That includes running the seismometer, other instruments, and moving our arm. So if we bring up K2, it'll show a timeline of what we're going to be able to do for the remainder of 2022. So during spring of 2022, we are going to be running our seismometer continuously, and that'll happen for another few weeks. We do have a couple of arm activities that we'd like to finalize. Those will be happening in the coming weeks as well. And shortly thereafter, we'll be placing the arm in a retirement pose. So if you look at the graphic below, the arm is kind of in an L shape. Our retirement pose is kind of in an inverted V, which allows the camera that's attached to the arm to be able to take images of the seismometer and the HP3 mole in front of the actual lander there. So it takes a lot less energy to run the camera. We'll be able to do that past spring. Now, towards the end of summer of 22, we anticipate our seismometer will be turned off, not because we want to turn them off, but unfortunately we don't have the energy to run it. We will be running it in various durations from continuous to approximately maybe like 12 hours to 6 hours per sol. But we do expect to end science operations at the end of summer. And again, at that time, we'll have lower energy levels, but we'll be able to monitor the lander power levels maybe once per sol or every other sol. And again, be able to maybe take a couple of images with the camera there. At the end of the calendar year, we do anticipate to conclude all of InSight operations. And again, that's just due to the lack of energy. So our operations team, we have a really bright team working on the project, and we were sitting there back in 2020, 2021 thinking about what can we do with this energy situation because it was predicted to decline. So we had a really clever idea of trying to figure out how we can actually clean these solar panels. And one of the ideas was using the Martian dirt to clean the dirt off the solar panels. So the idea was proposed. We all agreed, let's try this. I think this is going to work. So if you bring up K3, this is an animation that you will see where we use the arm to scoop the dirt, transport it over the lander here, and we slowly let the dirt fall onto the deck of the lander so that the dirt is carried over by the solar winds across the solar panels, cleaning it. Now, if you looked at the left-hand corner of that animation, originally started off orangish color, and when the winds blew the dirt over, it turned it into a more black color, allowing us to collect more energy there. So that was a really good cleaning. We've done this 6 times successfully. Doing this allowed us to continue to run our seismometer continuously for 4 to 6 weeks. So luckily, we've been able to do that so that we were able to catch that last Marsquake in the last few weeks. So that's really, really exciting for us. So, you know, it's an amazing team that we worked on. We've captured a lot of lessons learned based on all the challenges that we've endured on the Martian environment, and we're hoping that this will be carried into future missions. Here to talk a little bit more about that is Lori Glaze.
Great. Thank you, Katya. Yeah, so the InSight mission has really just been an incredible mission for us. It's given us a glimpse of Mars that we couldn't get from any other spacecraft in our NASA Mars fleet. An interpretation of the InSight data have really furthered our understanding of how rocky planets form throughout the universe, and in addition to just at Mars. So if I can pull up the graphic L1. I just wanted to remind folks that NASA's discovery program, InSight, is part of that discovery program. And as I said, it's not just telling us information about Mars, but broadening our planetary science understanding and helping us think differently about other rocky planets across the solar system and beyond. I think, understanding Mars and studying Mars's interior structure answers key questions about the early formation of these rocky planets in our inner solar system, including Mercury, Venus, Earth, Earth's moon, and Mars. And, trying to understand what they were like more than 4 billion years ago, as well as helping us understand rocky exoplanets. And we're just so lucky to have this great nursery of rocky planets nearby that we can study and help inform how we interpret data for some of the distant exoplanets, the thousands of distant exoplanets that we're discovering now, hundreds of which are, we believe, terrestrial or rocky exoplanets. So I wanted to say a few words about InSight's power system, thinking about it from the mission development perspective. For each mission, we decide what power source is most appropriate based on its science goals. Discovery class mission like InSight is very, very focused, and our goal really is to maximize the incredible science return that we can get from each mission. The principal investigator is responsible for making that happen. And one way to do that is to implement hardware that's flown before. The use of such heritage, we call heritage hardware, allows the mission funding to be used to help us get the most science that we possibly can out of each mission. And in the case of InSight, the mission's powered by those 2 solar panels that Katya was showing you. And those solar panels had worked previously successfully on the proven design of NASA's the Mars Phoenix lander, which flew before InSight. And so those solar panels on InSight were really only meant to provide power or designed to provide power for the primary mission. But I feel like we've been so lucky to get an extra year and a half of bonus science during the InSight extended mission. And so just thinking about those 3.5 years of primary and extended operations, you heard Bruce talking about some of the amazing science accomplishments that have been achieved by the mission. I just thought I would mention, a few of my favorite. First of all, I think the ability to see into the interior of the planet. This is something that we can try to do a little bit from orbit, but to overcome that constraint of only being able to see from the outside really required this seismic instrument on the surface of Mars. As Bruce said, he's been dreaming of for quite a long time. Secondly, the ability of InSight to determine the state of the core, the liquid state of the core, from the precise measure of the wobble of the planet as it spins. To me, that is just almost mind-blowing, just the level of precision that's required to get that measurement. And then finally, just using the seismic data as a means to learn more about the density and structure of the crust. To me, it's just been so cool, including that while the crust is perhaps thinner than expected, that there may be 2 or even possibly 3 sublayers within the crust. So finally, I want to wrap up by thanking Bruce and his incredibly dedicated team that met every challenge with innovation and creativity. They've had many challenges. Mars didn't necessarily want to cooperate in some cases, but this team was so creative over and over to come up with amazing ways to keep trying and not giving up on maximizing the science return. And the incredible legacy, as Bruce says, the legacy of this mission that's going to live on far beyond the lifetime of the spacecraft. They've found creative ways to use the scoop. You saw the video that Katya was showing picking up the dust with the scoop and rattling the dust off of the arrays, and a variety of other things as well. So I have a tremendous amount of respect for Bruce and his entire team. So if you can pull up graphic L2, I just want to, again, restate, as Bruce says, the legacy that these measurements and discoveries of InSight are going to hold for a very, very long time. They're unique and special, and we've made incredible advances in understanding the interior of Mars that are not likely to be improved for decades. And so as you kind of look at the sunset as viewed from InSight, we will think forward to the sunset of the spacecraft, but not the sunset of the science that's going to continue to come. Thank you.
Thank you, Lori, and thank you to all our speakers. We are now ready to take media questions. Remember to press *1 to get put in the queue, and please direct your questions to one of the panelists. We're also taking questions through the Ask NASA hashtag. If you are a member of the media asking questions and watching this teleconference on your computer, please mute your computer speakers before asking your questions, or else you will hear some feedback on the line. Up first is Marcia Dunn with the Associated Press.
Yes, hi. Can you hear me?
Yes, we can hear you.
Oh good. For Dr. Bannard, I'm just wondering if you and your team are already in mourning. There must be a sense of sadness about this. And when we think of Mars landers, we think of opportunity being taken out by this massive dust storm. And I know that wasn't the case here. Was it just dribs and drabs of dust over the years, just finally taking its toll? And lastly, for the German experiment, the mole, what's the bottom line on why that didn't work, do you think? Was it just an unlucky place to land dirt-wise? Thanks.
Okay, so first of all, there really hasn't been too much doom and gloom on the team. We're really still focused on operating the spacecraft. It's a full-time job keeping this spacecraft alive and operating and getting science on Mars, and we're still figuring out how to get the most science out of it, get the most data out of it, and every day we're figuring out how to optimize things. So we really haven't had time to really reflect on what's coming up, and that I think that'll probably come later this summer. So tune back in later and ask us how sad we are, and when we have time, we'll tell you. In terms of in terms of the HP-cube mole. The problem we had with that was that we ran into an unexpected kind of soil. We designed the mole to penetrate into sandy, unconsolidated soil, the kind that we've seen at Spirit and Opportunity before us, and even at the Mars Pathfinder site and Viking. So we thought we knew what we were going to be landing on, but it turned out the particular soil that was underneath InSight when we landed had a consolidated layer of crusty soil at the very top. And that crusty soil sort of disintegrated as the mole tried to penetrate, and thus was not able to provide the friction on the sides of the mole that we required to keep it from rebounding as it went down. And so the good news is we learned something new about the soil of Mars. The bad news is we weren't able to get down more than just to be able to bury the mole itself, and we weren't able to get our heat flow measurement that we had wanted to get. We were still able to do a lot of science with the mole, get some thermal measurements and physical measurements on the soil itself, but not being able to get that heat flow measurement was probably the biggest disappointment of the mission.
And as far as the problem with the dust, that's not from one big storm, but it's just an accumulation over natural dusting over the years?
Yeah, it's an accumulation, and we had predicted sort of the rate of accumulation based on previous missions, and it was about what we expected. What we had hoped for was that every once in a while the panels might get cleaned off by particularly high gusts of wind or perhaps dust devils, as happened with Spirit and Opportunity. But we're apparently in a place on Mars that doesn't have as many dust devils as Gusev Crater or Mariana Planum. So that just hasn't happened to us yet. It could still happen. There are lots of dust devils around us. We've actually been able to sense several thousand dust devils with our very sensitive pressure sensor that sees the dip in atmospheric pressure as they go by. But none of them have quite hit us dead on yet, enough to blow the dust off the panels. So we're still watching for that. We're not too hopeful, given that it's been 3.5 years and we haven't seen one yet, but it could still happen.
Thank you, Bruce. Up next, we have Elizabeth Howell with Space.com.
Thanks, everyone, for the time today. This is probably for Katya. You did provide a little bit of detail about what the ramp-down plan is going to be for InSight, but I was wondering if you could kind of give both a sequence for the instruments and a sequence for the science, especially after the seismometer is shut off.
So sequence for the seismometer, as I mentioned, the next couple of weeks we'll be running it continuously. In about 3 weeks, we're probably going to reach the threshold where we don't have the energy to keep it on continuously, so we'll be turning it on probably for a duration of maybe half a sol, and then maybe every other sol, depending on how much energy that's going to take. And we'll keep doing that until we just don't have enough energy to keep the seismometer on at all. Let's see. You had a secondary question? I'm sorry. Could you repeat that?
Yes, exactly. I wanted to know about the instruments and also about the science. Thank you.
Yeah, so the remainder of the instruments, our priority is to keep the seismometer on. So we will keep on the other instruments as long as possible. But once we no longer can keep them on, which is probably anticipated, summertime period, then unfortunately they will just be in permanent off state, and we'll be working with the instrument teams to do science closeout at that point.
Yeah, I can talk a little bit to the science. We're the science team has funding through the end of this fiscal year at least. We actually have our budget is set up to continue for about 6 months after the end of the mission to sort of finish taking all the data, preparing it, putting it in the archive, and getting our sort of final data products, our final Marsquake catalog and our final Mars models and things like that. So the scientists are going to be very busy even for another probably half year after the spacecraft itself is no longer operating. But that's just the beginning, because that data, as I said, is going to be available to the entire scientific community. Even now, we're putting our data into the publicly available archive every 3 months, and so our data is going into the scientific community with a fairly short, delay. We only take about, as I said, about 3 months to make sure that, we've taken out all the data errors and prepared it in the right formats and things like that. So that data is going to be out there, and scientists all over the country and all over the world can be using that data without any hesitation, from here on out.
Great, thank you. Up next, we have Marina Corin with The Atlantic.
Hi, this question is for Bruce or for Katya. Do you have a specific date or even a week that you're targeting for the end of operations, just something more specific than the end of the summer? And then I know you said you predicted the amount of dust accumulation that you'd see on the solar panels, and so you kind of knew what to expect. But does anyone on the team wish at the end of the day that InSight left Earth with hardware specifically designed to keep those clean and to give the spacecraft a longer lifespan? Thanks.
Bruce? Well, I answered the last question really well. There's a lot of things that I wish were on the spacecraft, and something to clean off the solar panels is pretty high up on my list. But whenever you put together a mission like this, everything is a compromise. It's just like, buying a car. I would love to have a top-end Audi or something like that, but my budget's more in the Volkswagen range. So, we put on the pieces of the spacecraft that would do the job that we needed to do, and we tried to figure out how to optimize that. And if we put more money into the solar array, we would have less to put into the science instruments. And so we tried to find the right balance. And whereas I would love to go to NASA and have them say, yeah, you have an unlimited budget, do whatever you want. But that would probably add a lot to the national debt.
Great, thank you.
The timeline for the end of operations?
Oh, would you mind repeating that again, please?
Oh, sorry. Yeah, I'm just curious if you have a specific date or even just like a week at the end of the summer where you're targeting the end of operations.
Based on our current energy level, I'm going to approximate mid-July, maybe early July. But again, summer is really what we're able to predict.
Yeah, and really, we're in an operating regime that we've never been in before. And so, as power goes down, we're not actually sure exactly how well the spacecraft will perform. It's exceeded our expectations just about at every turn on Mars, and so it may actually last longer than that. The other thing is that the weather is actually pretty unpredictable this time of year. We could have a little bit more dustiness. We could actually have a dust storm that could shut things down a lot sooner than we expect. Or it may not be quite as dusty this year as is average, which would allow us to go longer. And so there's an uncertainty in the weather at Mars. There's an uncertainty in just, how well the spacecraft will operate when it really gets down to the sort of the dribs and drabs of its battery life. So there's really too many uncertainties here to pin it down any better than that. We're hoping for more, and we're working to get it as much as we can, but we'll just have to see what Mars and InSight gives us.
Marina, thank you. I think those were both your follow-up questions. Up next, we have Bill Harwood with CBS.
Yeah, hey, it's Bill Harwood at the Cape. A question for Katya, if I could. Is there a way to compare the energy required to run the seismometer with something that might be familiar to people in their homes? Is it like a hairdryer requirement or a big light bulb, or I don't know what it actually consumes to get a sense of how much power you need to operate it. Thanks.
Yeah, so we actually did consult with our EPS experts on that to give people a more what is it really like here on Earth. So we kind of use an electric oven as kind of a marker to give people understanding. So when we first landed, it was about an hour, 40 minutes or so where you can run an electric oven. Nowadays, we could probably run that approximately 10 minutes max. So that'll give you a good understanding of how much energy is decreased.
Thank you.
And now we're going to take a social media question. Io on YouTube is asking, will seismometers similar to InSight be placed on other moons/planets in the future? Lori, would you like to take that one?
I would love to take that one. Yeah, I think, seismic measurements are so fundamental to understanding the interior, particularly of these rocky bodies or other kind of solid body planets. So we would love to put seismometers on a bunch of different places. For example, within the New Frontiers class missions that are included within the Planetary Science Decadal Survey, there's a recommendation to establish a seismic network on Earth's moon. That's been something that we've wanted to do for a long time. There were seismometers that the Apollo astronauts placed there, but they had limited operational timelines. We'd really love to set up a complete network on the moon to really understand what's going on there. There's also been a lot of discussion about other places in the solar system that would benefit from seismometers. For example, Venus is another place that would benefit from having seismometers and better understanding the interior there. Of course, there's unique challenges in that environment that might make that challenging. But again, as you said, I think there's a lot of scope for doing similar types of experiments on other destinations in the solar system.
Thanks for your answers, Lori. And we have one coming in from the username, the awesome Nintendo fan on YouTube asks, how are there earthquakes, we should actually say Marsquakes, if there aren't any plate tectonics there? Bruce, would you like to take that?
Yeah, that's a really great question. And of course, on the Earth, most of the seismic activity comes from the various different tectonic plates moving past each other and the rocks grinding against each other and sticking and slipping. But that's not all the quake activity on the Earth. There's also quakes that happen in the middle of plates. There's quakes that happen in the United States, in Colorado, in Oklahoma, even in North Carolina and Missouri. So there are quakes that happen in the middle of the plates, and those quakes happen because of forces in the crust. And those forces can come from various different sources. On the Earth, most of the forces come from the convection in the Earth's mantle, which brings heat up and drives the plate tectonics. But the heat that comes up in the mantle can dissipate itself in other ways. It can heat up the bottom of the crust, which can cause the crust to rise up, and that can cause cracking in the crust. It can cause the crust to be pulled apart in some places. As the planet cools overall and shrinks, it can cause compressive forces to build up in the crust, which can cause the failure of rocks, the cracking and motion of rocks. And so there's a lot of what we call tectonic forces, not just plate tectonic forces, but other kinds of tectonic forces that can build up in the crust of a planet besides with plate tectonics. And we believe that's what's happening on Mars. And in fact, we made a prediction as to how active Mars would be, how many Marsquakes we would see, just based on how quickly or how slowly Mars is cooling off. And our predictions are pretty much on the mark. And so certainly within the fairly large error bounds that we put on it. And so there's a lot of stuff that can go on in a planet besides plate tectonics that can cause these quakes.
Thank you. And now we're heading back to the caller line. Up next is Raman Skiba from Wired.
Hi, thank you. I have a question. I think it's probably best for Lori. I was wondering if this, what InSight has, what you've learned for future missions, like if there's, like for solar panel designs or like that, making them tiltable or, I don't know, shakeable or have like windshield wipers on them or anything like that, or anything else that about how InSight is informing future missions.
Yeah, it's a really great question. I think that's an area that will probably get some focus and some development over the coming years. Again, after the experience with Opportunity and then now with InSight as well, we know that systems that have solar panels are, that this is a challenge for these, that dusty environment. So I'm sure that there will be a lot of technology developments coming up on clever ways and thinking of ways that we can, try and keep those solar panels as cleared as we can. Other things that we can do is to think about the seasons in which we are sending our spacecraft. And, for example, in planning, for the Mars sample return mission, we're thinking about, trying to send the landers in a season that's less dusty, so that we have higher expectations of being able to get the most power out of the solar panels.
Thank you. And then up next we have Alexandra Weiss with Nature.
Hi, my question is for Bruce. I want to ask a bit more about this magnitude 5. I know that you're still working on analysis of it, but can you talk a little bit more about kind of the quality of data, like when in the day did it happen? Do you know it's a 5.0? Do you have any hints that you're going to be able to get location at some point? What might you be able to learn about that magnitude 5?
Okay, so this magnitude 5 quake, what we call a S1222A, that's our name for it, it is so far and away bigger and more clear than anything else that we've seen. It actually happened early in the Martian morning during a relatively noisy part of the day, but it was such a large signal that the noise as you saw in that first animation, the noise was just like a single line. And in fact, the largest quake that we saw before that would just have barely been a blip. And so the background noise on Mars really didn't matter to this quake at all. It was the signal was so large that it just completely swamped whatever background noise we have. We have a very clear P wave arrival, a very clear S wave arrival. We have good polarization, so we're getting a really good determination on the location. We can actually see with our eyes, you can see surface waves in the spectrum, which is something that we've been struggling to find in previous quakes through the whole mission. And so they're really booming out in this, and we'll be able to do analysis on that. This quake is actually big enough that we think it's right on the threshold where we may actually be able to see the free oscillations, the normal modes of Mars excited, which is something that happens with the larger quakes. It actually sets the whole planet ringing, and we can look at the resonances of the planet to say something about its structure. And so this quake is really going to be a treasure trove of scientific information when we get our teeth into it.
So where does it come from? What is the location?
The location is near Cerberus Fossae, where we have gotten a lot of our quakes before, but it's not actually in Cerberus Fossae, which is interesting, and we don't really understand that yet. Like I said, we've only been looking at this for less than 2 weeks now, but we're pretty sure that it's not on the fault system in Cerberus Fossae. So where it's actually the origin of it is not known yet, and we're still analyzing it. But it's in that general part of the planet.
Thanks.
And up next on the phone lines is Kenneth Ching with the New York Times.
Hi, thank you. I had two questions. One is for Bruce. What did you lose by not having the mole fully deployed? What science questions were you hoping to answer that are still unanswered? And then for Katya, is there any chance that it could come back to life after the end of mission? And if so, would anyone be listening for it? Thank you.
Okay, so the science goal we had for the HP cubed instrument was to actually measure the heat flow coming out of Mars. We're going to measure the thermal gradient and the thermal conductivity to get the amount of heat that Mars is losing, and that would tell us something about both the interior temperatures on Mars and the degree of energy that's driving the internal geology of Mars today. And that's something that it was complementary to the structural information we're getting from seismology. Seismology tells us sort of what the building blocks of the planet are today, and the HP cubed was going to tell us something about the dynamics of it. We can get some of that information from seismology. We're actually able to put constraints on the thermal profile in the mantle. We can put some constraints on the temperatures in the core. The HP cubed was going to help us to nail that down a little bit more precisely, and so that's what we lost. When we proposed the mission, the HP cubed was proposed as a secondary instrument. We knew that there were challenges involved in it. We knew that the mole was a sort of a cutting-edge type of instrument and apparatus that we couldn't guarantee was going to work on Mars. And so when we proposed it, It was part of the so-called baseline mission, but not the threshold mission. And InSight was actually selected on the threshold science goals, which all had to do with either seismology or the precision tracking. And so we were able to basically have a technically fully successful mission without the HP cubed. We got the most important science goals with the seismology and the precision tracking, but it was definitely a big scientific disappointment for us.
And up next on the phone lines is, Katya, you have next.
So yeah, to answer your secondary question is, can the lander be operable again at some point? So as Bruce mentioned, the Martian environment is very uncertain. We don't know what's going to happen. However, if we were to have a natural cleaning and the solar panels were able to actually be cleaned off and we're able to get enough energy, our lander may be able to communicate back down to Earth. So we'll be doing what we call open loop recording after the lander is no longer able to communicate with us, in the event that there is a cleaning. Like I mentioned, it's a natural clean that needs to occur on Mars to be able to do that. But we'll be listening, and once we get a few beeps, if that happens, again, if there's a natural cleaning, then we will evaluate whether there's enough energy to have the lander operate again. So that's to be determined. We're hopeful. That would be awesome.
Thanks. Just trying to get through everyone in this caller line. Now we have Jonathan O'Callaghan up next.
Hi, thank you. Yeah, a couple of questions for Katya or Bruce. I'm just a little unclear on what will take place between the end of summer and the end of the year. Could you just spell out what the lander will be doing specifically? Will it be taking pictures or anything like that? Are there any options of, rather than running the seismometer continuously, running it intermittently, for example, at night when noise levels are low, to prolong the time it's active on the surface? And just one more, going back to Laurie Glaze, could you just spell out a few more other worlds that you think you might want to use seismometers on, aside from the Moon and Venus? Are there things being considered, like Europa or any other destinations? Thank you.
So I can touch on the first part of your questions there. So yes, during summer, as I mentioned, our primary objective is to run the seismometer on continuously. We are also going to be able to take some camera images of the workspace, so looking out towards the seismometer and the HP3. That takes a lot less energy to do so. But in addition to running the camera and the seismometer all the way to the very end, we're not going to be able to do very many other science operations. And at that point, it'll be just telecommunications with the lander through end of calendar of 2022.
Yeah, and to your second question, this is Lori, thinking about seismometers. I forgot to mention earlier, of course, Dragonfly is carrying a seismometer going to Titan. So that will be, I think, a fantastic addition there. Of course, Titan is or the Dragonfly mission is a very different type of operation where it's moving around, but still being able to have an opportunity to detect Titan quakes will be very valuable. Right now there is not any specific plan for a lander on Europa, but certainly something like that I think would be incredibly valuable. Again, any place where we can land on one of these solid body surfaces and get a sense of what's going on in their interiors would be extremely valuable.
Yeah, and I'd just like to interject that I feel like, InSight, one of the InSight's legacies is to really prove the technique of seismology for planetary science. The last seismometer that was sent to another planet was on Viking back in the mid-'70s, and that seismometer was not successful. And I think that kind of cast a pall over planetary seismology for almost 40 years. Seismology is a difficult experiment to do in space. It's a difficult instrument to build. But I think, InSight has sort of, finally cleared the air and shown seismology for the incredibly capable technique that it is.
Thank you. Up next on the phone lines is Becky Ferreira.
Oh, hi. This is a question, I guess, for Bruce or Katya. You mentioned that there's unprecedented data also on weather and magnetic fields and planetary rotation from InSight in addition to the seismological stuff. So could you kind of give an overview of those other instruments?
Yeah, I can take that. So InSight had three primary experiments that it was proposed to do. One was the seismometer, which was the main one, and we've already talked about the heat flow experiment. And then RISE, which is this radio science experiment, was put on board to measure the details of the rotational dynamics of Mars. So actually look at the motion of Mars's rotation pole, its north pole. That's been an extremely successful experiment as well. We've already published an update to the moment of inertia of Mars, which gives some constraints on the size of the core. But the real goal of this experiment was to try to measure the nutations of Mars, and we're still analyzing that data. We have some papers that have been submitted, which are still being peer reviewed. So I can't talk about the results yet, but we've gotten the data that we had set out to get, and we believe that we're seeing the signal from the core of Mars, and I think we'll find that that experiment will give us some additional constraints on the size and the composition of the core. The weather station and the magnetometer were in the interesting position of not being proposed as instruments, but they were put on just as sensors to detect noise that would be affecting the seismometer. So originally we didn't have any science goals, any formal science goals associated with those instruments, those sensors. They were there to see if we saw magnetic oscillations that we could tell whether those were interfering with the seismometer's operation, or when there was wind, pressure variations, and so forth. We could be able to detect those on our pressure sensor and our wind sensors and be able to discount those kinds of signals on the seismometer. But meanwhile, scientists being what they are, they're taking that data and doing an amazing work with it. I mean, we actually put on some really capable sensors. The magnetometer that we put on is the first magnetometer to send data back from the surface of Mars, and we were able to both put constraints on the magnitude of the sort of the background magnetic field at the surface, which was much larger than we expected from orbit. We were able to look at the magnetic variations at the surface of Mars, mostly due to ionospheric currents in the upper atmosphere of Mars, and relate those to solar wind activity and to the dynamics of the ionosphere, and that's really unique data that's been used in conjunction with other magnetometers on orbiting spacecraft to better understand the magnetosphere of Mars. The weather station has taken a really detailed series of measurements of the Martian weather at the InSight location for about 2.5 years. It's been a little bit spottier for the last year as our power's gone down, but this is probably the most precise and high resolution pressure measurements that have ever been taken at Mars, which has allowed us to look at various different activities of weather fronts, of something called a bore wave, which was something that's never before seen on Mars. Looking at, as I said, we can have been able to sense thousands of dust devils using our pressure sensor, and also our seismometer actually is able to see dust devils as well, looking at sort of the tilt of the ground that they cause as the low pressure center of the dust devil moves within either tens to hundreds of meters from the lander. The seismometer can actually see the tilt of the ground from that, and so there's a whole myriad of scientific questions that have been addressed by the other InSight instruments over the course of the mission.
Thank you.
Up next on the phone line is Lauren Brush with The Verge.
Hi, thank you for taking my question. I think mine is for Bruce. Just now you said that you were able to sense several thousands of dust devils nearby InSight, but earlier you said none have been dead on. I'm just wondering if you know why that is the case. Does it have anything to do with the lander's location, or is it just bad luck? And also, given the challenges that the mole had with the soil, are you still happy with the landing spot that you picked, or would you have landed in a different spot knowing what you know now? Thanks.
Okay, so as far as the dust devils are concerned, like I said, we can actually sense these dust devils out to many hundreds of meters away from the spacecraft, and so just looking at the statistics and the sort of the width of dust devils, which are pretty narrow for the size that we're looking at, it actually takes a pretty precise aim to actually hit the spacecraft with one of those. So I think it's just, if you look at the statistics of the number of dust devils, their distribution of speeds and spacings across the planes and their width, I think it's not it's not unlikely that we haven't actually had a direct hit. And it looks like our inference is that it actually has to pass right over the spacecraft itself in order to do any good. Even a near miss doesn't really help us much. And we've seen, actually, you can see dust devil tracks on the surface that have been caused by dust devils moving past us, just a few tens of meters away. And so some of them will come pretty close. Another interesting fact is we haven't actually ever seen a dust devil with our cameras, and so many of these dust devils might be dust-free. They may just be vortices, or just whirlwinds without actually any dust in them. And so that's just another interesting fact. Let's see.
And then your landing spot. Are you still happy with that?
I'm still really ecstatic about the landing spot because it allowed us to land safely, and that was the primary goal of our landing site selection, was to find a place where we could land safely. Landing on Mars is one of the most difficult operations in planetary science. It's been done successfully several times now in the last decade or so, but if you go back further, you'll understand just how difficult that was. And so with the seismometer, which was our main instrument, the beauty of that was we could land anywhere on the planet and still do our science. I mean, when you're trying to look at the core, anywhere you land, the core is going to be right under your feet. So that sort of was taken off the table in terms of driving the landing spot. And we really were looking for some place that was flat, without many rocks, where the lander could land without any danger, and I'm still, just really, really glad and thankful that we were able to land safely. And so I wouldn't trade that back for a risk of landing, and having the possibility of not having any of this happen.
Thanks. Up next on the phone line is Lucy O'Borg of AFP.
Hi, thanks for doing this. For Bruce, again, could you try to sum up what we've learned so far on Mars' core, mantle, and crust? I know it's difficult, but what we didn't know before that we know now, thanks to InSight, kind of the main findings. Thank you.
Well, the thing was, before InSight, the interior of Mars was kind of just a giant question mark. I mean, we knew that Mars had an iron core. We knew that it had a crust. But, for example, the crust, it could have been anywhere from 20 kilometers thick to 120 kilometers thick. The core had an uncertainty of, plus or minus 200 or 300 kilometers. And so, we just had this really fuzzy picture of what was going on inside Mars. And I think InSight's real contribution is now we can actually draw a quantitatively precise picture of the inside of Mars. We know what the thickness of the crust is to within about 10 kilometers. We know what the size of the core is to within better than 50 kilometers. And I think we'll be able to actually improve on those numbers as our analysis proceeds. And the importance of those kinds of precisions are that they allow us to now go back and look at our models of planetary formation, look at how the planet evolved from just a cloud of dust that was circling around the sun as it coagulates into a planet, starts to heat up and melt, and then differentiate, separate into a planet with a dense core at the center, a low-density crust at the surface. How that process works is something we know that planets do. We know a lot about it, but the details of that process are very, very difficult to understand in a laboratory, on the surface of the Earth. The best laboratory is actually the planet itself, and InSight is actually able to go to the laboratory that is Mars and make the measurements of what the planet was that resulted from this process. And we've already been able to to eliminate probably 2/3 of the models for planetary formation that are out there just by looking at the size and the density of the core and the thickness of the crust. And that's just with the data that's been published just in the last year or so. So this is just beginning, a process that's beginning. And so I think what InSight's done is it's actually shone a light on the inside of Mars, whereas we've known a lot about the outside of Mars. We've taken images, we've taken spectra, we've made measurements on the surface of Mars, for the last 50 years. InSight's the first mission that actually shone a light beneath the surface of Mars and showed us what the rest of the planet looks like.
Thank you.
Great, thank you. Unfortunately, that is all the time we have for questions. If you're a member of the media, you can contact the JPL Digital News and Media Office if you have additional questions. We'll also try to answer as many social questions we have. The operator will provide the phone number on the media telecom line, so stay tuned. And then for more updates on the mission, visit mars.nasa.gov/insight. You can also follow us on social media at NASA JPL and at NASA InSight. We'll also have a video that summarizes InSight's journey to wrap up this teleconference. Members of the media can watch the video and a replay of the entire teleconference on our YouTube page, which is youtube.com/NASAJPL. Images from today's teleconference with sound will also be available at jpl.nasa.gov/insight-update-telecon.
Thank you for joining the telecom. You have
touchdown confirmed.
InSight has been fantastically successful. We've gotten more science than we had ever dreamed that we would get during the course of this mission. InSight's primary goal was to better understand how the terrestrial planets, the rocky planets, formed and evolved.
First, we landed an incredibly sensitive seismometer on the surface of Mars, and with that, we were able to record over 1,300 Marsquakes.
And these range all the way from tiny little tremblers that just barely go over the noise background to a handful of quakes that were larger than magnitude 4.
And feeling those vibrations, the scientists can actually take that information and use that to reconstruct all the material that those Marsquakes traveled through and thereby see the interior of the planet.
We looked at its core, which is big and not very dense. We looked at its mantle, which is not so hot. And we looked at its crust, which is not too thick and not too dense compared to some of our pre-mission expectations.
By measuring the detailed structure of the inside of Mars, it gives us a snapshot of what the planet looked like 4.5 billion years ago. The other thing that we've been able to do is make a very detailed record of the weather at Mars. So we have a really good weather station, which has allowed meteorologists to study the weather at the InSight landing site and relate that to the climate changes on Mars.
What we didn't do, unfortunately, was make the heat flow measurement we wanted to make. Our heat flow probe was supposed to get 3 to 5 meters down, and we were unable to reach that depth.
But we were able to get some of those measurements, such as the heat transfer amongst the soil.
InSight is a solar-powered mission. We have solar panels, and they were designed to give us enough power to easily get through the first 2 years.
But there's a lot of dust in Mars' atmosphere, and that's falling down on top of our solar arrays and slowly blocking the sun.
As the panels are getting dustier, we started racking our brains with whether there's anything we can do to try to clean off those panels ourselves.
When the idea of using dirt to clean the solar arrays was first proposed, it seemed counterintuitive.
We were actually able to use the arm and the scoop to scoop up some soil from the ground and dump it over the lander, having some of that heavier sand blow onto the arrays and knock some of the dust off. So we essentially used it as an array cleaning tool.
Cleaning with dirt actually worked.
It allowed us to actually keep the instruments going during the low power season where the Mars is farthest from the sun during the winter. Unfortunately, later this summer, we think that the power is going to be dropping so quickly due to the atmosphere getting dustier, due to the alignment of Mars and the Sun.
We're going to be at a point where we can no longer have all of our instruments on, which means we'll be turning off the seismometer and other instruments on board.
The last day is going to be bittersweet. Obviously, we're preparing for it. We know it's coming. But that first moment where we don't hear from the lander when we expect to, that's going to be tough.
It's left a permanent mark on me. I literally tattooed InSight onto my arm. I'll never let it go.
We've really rewritten sort of the chapter of the encyclopedia on the interior of Mars. That was our last big hole in our understanding of the planet.
There's a lot of data that people are going to be looking at for decades to come.
We accomplished so many of our science goals, and we're going to have something to look back on and be proud.